and we're gonna get started. Um, we're gonna talk today about desalination as an example of a case study, and then we're gonna look at the other case studies that folks have been thinking about in with respect to concentration and water. And then we're gonna talk about your community water project. So, desalination is this process of removing salts or minerals or other contaminants from seawater or brackish water or even wastewater effluent. And it's a fairly global common solution to being able to obtain fresh water for human consumption and for domestic or industrial use. But obviously, there are some challenges that come with it. So, this image is an example of a plant and its discharge. And you can imagine that the discharge is a concentration issue. So, what are you discharging? What's the concentration of what you're discharging? And where are you discharging it? So, I want to give a little bit of context. So, the World Health Organization says that every person needs guaranteed access to at least 15 liters of water per day, preferably all drinking water or at least fresh water. And that's an access question. Um, According to the World Water Institute, there are almost 2 billion people in 17 countries that are either already in or headed towards an acute water crisis. So, conventional sources of water, rainfall, snowmelt, river runoff that we see in lakes, rivers, or aquifers aren't enough to be able to meet the human demands for water, particularly in areas that are water scarce. So, I thought these statistics were really interesting. So, 1.4 million cubic meters is the amount of fresh water that's produced per day by the world's largest desalination plant that's in Saudi Arabia. 100 million cubic meters is the fresh water that's produced per day by the roughly 20,000 desalination plants that are. And about 40% of the world's population is affected by the scarcity of fresh water or potable drinkable water. So, um, the California Coastal Commission is the legal mandate that protects the coastline of the United States, and in this case, California. And they denied a building permit for a large seawater desalination plant. So the application to build the plant was made in 2013. And this is an example of a project that really divides experts, politicians, activists. So the 190 million liters of drinking water that the plant would have generated every day is held in the scale or weighed against the environment or the potential consequences of the use of that plant and the damage that it would cause, including the marine life that are found in about 275 million gallons or about 1 billion liters. So this is a fraught issue. To give us a little bit of a sense of why it's an issue, we're going to look at a scaled mock-up of a desalination plant. So there's the seawater intake. Usually this is subsurface and in the ocean, open ocean. There's the pre-treatment that occurs. So typically this is filtration and then coagulation of other solids and filtration again. Usually it's membrane based. And then there's reverse osmosis, where we'll talk about modules that essentially have very specific membranes to separate the water from solutes. And then there's post-treatment, which ironically is remineralization, so adding back in ions that are desirable, but also removing things that affect taste like boron and chloride, and then disinfection to make sure that, in fact, it's safe water. And then the consequence of all of that work is a brine discharge, where it's typically also offshore, and usually it's diluted because to discharge it as concentrate of the brine would literally kill sea life. And usually it's multiple ports of a diffuser that release that back into the ocean. So you can imagine There are a number of concerns that come with a desalination plant, and several factors that have to be considered, not just the energy use, but also the potential for pollution, as well as um, the actual process itself and the generation of drinkable or potable water. So, at its most fundamental level, desalination is this process of removing salts or other minerals and contaminants from seawater. The challenge, right, is that it consumes both a substantial amount of thermal and electrical energy, which has the emission of greenhouse gases associated with it, and um, there are problems with pollution as a result of the discharge. So if we think about it just in terms of energy, here's an example of the power consumption. Early desalination plants consumed huge amounts of energy. Since then, they have been optimized, but they still require a significant amount of energy. Um, the image on the right shows the minimum amount of energy and the percent recovery to remove certain types of salts and the concentration of those salts. Essentially, you have to put energy in to power a pump, and then you have to use that pump to push water through a reverse osmosis module, which results in the purified water, but also the generation of the concentrate that includes high levels of undesirable ions. So when they do a reversible thermodynamic process, the energy is going to be equal in magnitude but opposite in sign to the free energy of mixing. So this means that we're thinking about things like osmotic pressure that we've talked about previously. And the free energy of the mix is something that we can calculate where we know the ideal gas constant, we know the temperature, we know the activity of water, we know the number of moles, and we can calculate the osmotic pressure. So we could determine the amount of energy that's actually required to run these plants. So let's think about that. The theoretical minimum energy of desalination for seawater is 35,000 parts per million salt at a typical recovery of 50%. So that amount is 1.06 kilowatt per meter cube. The actual energy consumption, though, is going to be larger because desalination plants are finite in size and they don't actually operate as a completely reversible thermodynamic process. So additional energy, greater than 1 kilowatt per meter cubed, is consumed by the intake, the pretreatment, the post-treatment, and the brine discharge. So most of the desalination plants consume somewhere between 3 and 4 kilowatt per meter cubed, and they emit 1.4 to 1.8 kilograms carbon dioxide per cubic meter of water that's produced. So you can start to think about the amount of carbon dioxide that's generated when you're using a desalination plant. So who does desalination? Well, there are large-scale seawater reverse osmosis desalination plants that have been constructed in Spain and in Israel, mainly in the arid Gulf countries. They use thermal desalination, where seawater is heated and then the evaporated water is condensed. In South Korea, there's some really interesting research around hydrothermal heat pumps that use solar energy to help boost desalination production and to improve efficiency. So there are multiple countries that are doing desalination. So how does the reverse osmosis work? So this water treatment process removes contaminants from the water using pressure through to force the water through a semi-permeable membrane. The membranes have water permeabilities that range, and they actually are highly effective. They can reject 99.6 to 99.8 of the salts that are dissolved in the seawater feed, and that's a really important um, thing to notice. So normal osmosis, right, is water moving across a semi-permeable membrane to dilute a concentrated solution. In this case, reverse osmosis does the opposite. It takes a concentrated solution and by forcing external pressure, pushes the water through to create essentially fresh water and leave the ions in a more concentrated form behind. So you might be wondering, well, what kind of semi-permeable membranes do this work? So this is some really interesting chemistry. The diphenylene, diamine, trimethyl chloride form a cross-linked polyamide, and it's this polyamide and other forms like polyethylene oxide or zwitterions or sugar-derived or polyglycerols that have different surface properties that then impact how easily they move water through and keep the ions behind. So I said there are multiple countries that are invested in this work. There are a variety of examples here. Um, One of the things we're going to take a look at next week are some of the innovations in desalination and the chemistry associated with that. But sufficient to say, a number of developed countries are highly invested in this as technology. So, a couple of examples for us before we take a look at our case studies. So, Saudi Arabia leads the globe in the production of desalinated water. They produce daily 117 million cubic feet. They have 27 plants spread across their coastline, with 21 along the Red Sea and 6 on the East Coast. They use two different processes that are kind of multi-effect distillation, and they do have some that are reverse osmosis that use a multi-stage process. The United Arab Emirates has very scarce fresh water, and they have a freshwater per capita demand of 650 liters per day. So their primary source of fresh water are aquifers, but most of the water from those aquifers is saline. So sometimes having 8 times more salinity than salt water. So it's not fit for human consumption. So the Abu Dhabi-based government has invested significantly in desalination of seawater. They have 8 desalination plants at a cost of over 3.2 billion, and they're run by government foreign investor partnerships. Another example is Kuwait. So they have 0 permanent rivers, and so it relies exclusively on desalination plants for fresh water. They were the first country to establish desalination for large-scale supply of clean water in 1951. Their current desalination plants produce 58.3 million cubic feet. 52 of that is generated through flash distillation, and then 6 is produced through reverse osmosis. And interestingly enough, they have government commissioned water supply system and storage um, specifically to help address the water needs of their population. So today we're going to spend some time looking at case studies and thinking about how do we analyze water at a specific regional location. So the case study example that I'm going to share today is Monterey Peninsula. So the problem is that historically the Monterey Peninsula received the majority of its water from the Carmel River. But to protect some of the threatened species that live in the river, the California State Resources Control Board reduced the amount of water that California American Water, or CalAM, can produce from the river. So the only other source of water is the Seaside Groundwater Basin, and that's also under a court-ordered reduction schedule to protect the basin from overuse and prevent seawater intrusion. So the reality is there's a high need for water, but there's a low supply. So currently, the water use for residents of the Monterey Peninsula is among the lowest in the state, and we actually use about half the water that was used residentially in the 1980s. However, the ordered cutbacks to the existing water supply um, mean we have to find other sources of water. We just don't make enough water for the need. So, because of a combination of factors, the peninsula is facing a significant water shortage. Um, California has been contending historically with drought in spite of the atmospheric rivers. And, right, there's also the need to protect, say, for example, ecosystems such as the Carmel River. So there are restrictions on water use, which can go only so far. And maybe more importantly, where folks really started to notice this is because there was a moratorium on new construction. So in order to build, you have to have access to additional water. And so way back when, in April 2012, CalAM submitted an application to the California Public Utilities Commission to create projects to try and address this problem. So, what's some data that helps us make sense of this problem? So, right now, um, between October 1 and September 30th, 2024, the most recent publicly available data, there are 8,972 acre feet that were pumped into CalAm's system in the past water year. So while this is the lowest since 1977, which was probably the first time that there was rationing for water due to drought, um, it's important to note that we are still going through a period of drought. So on the left, you can see, say, for example, the visualization associated with when there were atmospheric rivers and the fact that while there was new fresh water, there was still significant amount moderate drought as well as severe drought. But right, if we look at other time points when there have not been um, atmospheric rivers, the drought is considerable. So while we have variation over time, what I want to show you on the right is information from the National Integrated Drought Information System from NOAA. And this shows the percentage of California land that is experiencing drought. And we have categories similar to what's shown here, that's abnormally dry, moderate, severe, extreme, and exceptional. And what you can see over time is while there is variation, we are certainly, as of 2025, still in a period that would be considered drought. So the lack of water due to rainfall or inconsistent rainfall is maybe a better way of saying that, is still the case. The other piece of data that's really important here is something called saltwater intrusion. So we're going to pause for a minute and just take a look at this visual and do a couple of things to orient. So we have our compass points west and east. So if you're looking at this image, our ocean would be here on the left. There's our Monterey Bay. You can see the salt water waves. And this is our seawater. And you can actually see, right, the concentration in milligrams per liter. Then we have our land surface. We have a pretty deep bay. So there are a couple of really key points here. So there's the land surface, there's the Salinas Valley aquitard, there's the groundwater level in our aquifer, there's fresh water that's available, and then there's the groundwater level in the 400 foot. So these are varying depths. And then this would be, say, for example, the depth of fresh water. And then this is our transition zone. So if you think about it, right, saltwater intrusion simply says, look, there's water that's coming in from the ocean, and that is intruding, right, on the fresh water that's available in the aquifers. And so that's a problem because we use fresh water, say, for example, to water crops, to grow lettuce or spinach or broccoli, as well as pumping water from the aquifers for residential or industrial use. So those are examples of data that inform this problem. All right, so what are our proposed solutions? So there were three solutions that were proposed. The first one was desalination, the second was aquifer storage and recovery, and the third one is groundwater replenishment, or essentially repurifying water to be able to reuse it. So what does that really look like? So we've talked a little bit about desalination. For this case study, it would be subsurface slant intake wells, the building of a plant in marina, and then the facilities, say for example, the pipelines, the brine disposal facilities. And so all of this was conditionally approved in November of 2022. But there were a number of steps that had to be followed before they could actually acquire the building permit. That required a number of approval, including, say, for example, approval from the city of Marina. The other two projects were the aquifer storage and recovery. So this is in partnership with the Monterey Peninsula Water Management District. So this is where excess flow from the Carvo River gets stored in Seaside and the aquifer. And then during the summer or the really dry months, then there's greater withdrawals. So winter flows, though, are considered in excess only when they exceed what's necessary to protect the Carmel River's threatened population of steelhead trout. And then the third project is Pure Water Monterey, which is a partnership with Monterey One Water. And it recycles wastewater through an advanced treatment process. So gray water is water that um, could be either storm runoff, but it could also be wastewater. And so this water is purified and then it's injected into the seaside groundwater basin. And this is actually what provides 1/3 of the peninsula's water. Um, when they're done with their construction this year, it should provide over half of the water that's required by the peninsula. So these are some of the solutions that are in play, but the reality is neither Pure Water Monterey nor the aquifer storage and recovery is sufficient to meet the needs, which is why desalination has been proposed. So it's important to notice here that there's some complexity. So um, there are documents that go through a review and approval process. Um, an example is they actually have to undergo legal review by the local superior court and board review. So that's one example. But it gets more complex. So there are bench trials that are lawsuits where they say, look, you can't buy and or use um, and some of those have political arguments behind them. Some of them are fact based, but interestingly enough, the Monterey Superior Court um, hears these arguments and then makes a ruling. Here's a brief timeline, except the timeline's not that brief, it's actually quite long. So in 2019, the Marina Coast Water District sued the county for granting a permit to build the desal plant in Marina. They allege that building the plant would violate essentially the Environmental Quality Act and that there are records that it would cause harm. In 2021, um, a judge who is now retired threw out two of the Marina Coast allegations, but agreed about the overriding considerations. So it was deemed a victory for the Marina Coast, and there were no approvals. Then in September 2023, Cal-Am had their attorneys um, essentially file an appeal and they reversed the judge's decision. As of May 9th, 2025, two judges adopted Cal-Am's demand estimates and their current supply, um, paving the way for approval and potentially the permits being granted to build the desalination plant. So as of now, the systems are go to get the plant built, although there are other conditions that Cal-Am has to meet. So they are trying to have an operational plant by 2027. So this supply demand analysis was really key because that made the determination that there's enough demand to meet the need for constructing the plant imminently because the need for water is acute. So all of that is a great example of a case study that shows um, a need. I've got a couple of other examples. So um, you had a choice of three to choose from. Um, so I'm going to go there and we're going to take a look. So the first one that we had was Weedron. Let me make sure that I open this up big enough. So let's just take a moment and read a little bit about Weedron, and then we'll talk about this case study. And you have access to this on Canvas too. Okay, so similar to what we discussed with the desalination, we're going to think about what's the problem, what might have caused the problem, and then how did the problem come to the attention of residents, the local government or state and US EPAs, and then what data would you want to be able to assess and address the problem? So, can I have someone who read through this case study share a little bit about their thinking?
Can you hear me?
I can go for it, Reese.
Okay. So the problem was that the residents of small town Weedron, Illinois, reported gas-type odors from their private well water, and the study from 1982 to 83 confirmed the presence of volatile organic compounds that are commonly associated with gasoline, such as the carcinogen benzene. And then for the cause, the source of contamination was found to be an abandoned underground storage tank that stores gasoline from former gasoline stations. And the Weedron sand mine and attendant facilities had a role in altering the direction of groundwater flow and also contained leaking gas storage tanks, but were found to be unlinked to the residential wells, but were also considered for possible silica contamination. And then the problem was brought to attention by reports from the residents originally from their own groundwater, and they brought it to the attention of the Illinois Department of Public Health. And after finding alarming levels of benzene in their water, the county health department told residents not to drink the water, and then they alerted the Illinois EPA, which alerted the US EPA to begin investigation. Um, if I were to do, or if I were to assess the problem, I would want groundwater samples to test the chemical composition and presence of volatile organic compounds, semi-volatile organic compounds, and metals, and compare them to the health standards.
Awesome. That's a phenomenal overview of that case study. That's an exceptional job. Well done. Okay. The next case study that we're taking a look at is the Salton Sea. I'm going to give us a little bit of time to read. And then, just so you know, if this was the case study you selected, you're going to be on board next to give us an overview. So let's take a minute and read. Okay, can I have someone who read the Salton Sea case share what's the problem, what might have caused the problem, what data do you need, and how might the reek or the smell provoke human outcry, and then how are non-human agents impacted?
So the problem with the Salton Sea is that it's become less habitable for migratory wildlife that depend on it, which includes over 400 birds. The cause is largely due to runoff from the Imperial Valley, which the Salton Sea relies on to maintain its water level. But as we are in a drought and water is much more valuable, farmers have become a lot more efficient with their water usage, so there's less and less runoff. Additionally, climate change, as it gets hotter, there's more evaporation, the water level lowers, and the salinity rises, which kills fish that the birds depend on. So essentially, the water is evaporating at a faster rate than it's rising. It's
Mhm.
rising. And then the data that I would want would probably be water quality and water level over time. And I would probably want to look at if there was like additional water sources that maybe we could use to get the level to rise.
Mhm.
Um, and so the reek of the Salton Sea working to provoke human outcry is, I think it's kind of ironic that it's genuinely like the smell of death. It's
Mhm.
sulfur, it's like rotting eggs, but it's also the dead fish. So
Mhm.
it's also in the article, it says that it's in waves, which means that you can't ignore the smell. So it's like waves of death that are trying to, they're more annoying. So it's more likely that people are going to want to do something about it.
Mhm.
And then the last part, um, I think that because, okay, humans don't care as much about environmental change if it's not affecting them.
Mhm.
So I think birds that only use it, like they're migratory, so they don't use it all year round, and fish are not that important to humans, or
Mhm.
at least they're not on the forefront. So I think that's how they're typically ignored.
Yeah. I think it's such a great example of a problem that comes to someone's attention because it's a change from the normal. And then there's all of this like searching for the cause when it's actually a fairly well established problem that largely is ignored until it generates this horrible smell. So, thank you. That's a really powerful overview. I feel like the Salton Sea is a harbinger, a bit of a warning space of what can happen if we don't address a problem and it is allowed to persist. Okay, the last one that we have is a more contemporary example, and that's Pajaro and the flooding. So let me just pull that up. I'm going to give us a couple of minutes to read, and then if this was your case study, we look forward to hearing from you. So let's take a couple of minutes just to review this case. Ooh, sorry, I went too fast. All right, so here are our discussion questions. What is the problem? What might have caused the problem? What data would you want to assess and address the problem? How might the flooding be the result of climate change? How does this flooding impact humans? And how are non-humans impacted, implicated, or ignored in the ecological perceptions? So, would love to hear from you if this was your case.
Hi, okay. Can you hear me all right?
Yeah, you're great. Go for it.
Perfect. So the problem was the flooding destroyed thousands of homes and roads and all of that. The cause of the problem was the flooding, the lack of flood control. There was less vegetation, rodent control, slope rehabilitation, and the data that we would want to assess and address would be things such as that, like the sorry, the amount of vegetation and trees being removed in the slope rehabilitation, like we would want to see how we could solve issues such as that. And then how is the flooding the result of climate change? So like I think it was Sydney that said increased evaporation,
Mhm.
which leads to more atmospheric moisture, heavier rainfall, and then the rising of the sea levels, which caused the flooding.
Yep.
Um, and then how does this flooding impact humans? Obviously, it had destroyed many homes. Thousands of people were under evacuation. It's hard to ignore an issue such as flooding when it is at your doorstep, quite
Yeah.
literally. And then how are non-humans impacted, implicated, or ignored in the our ecological perception? So other than the obvious, hey, the animals also live here. If we are living here, um,
Mhm.
it also affects the animals that might have lived in the rivers and the trees, stuff like that. The rodent control that they were trying to work on was also affected by and it's a lot of physical damage to their ecosystems. So,
It's a great overview. Thank you, Megan. I feel like one of the pieces that I hope these cases highlight is that these are complex, right? Rarely is it just a single point of impact, right? An example like the Pajaro atmospheric rivers and the flooding that occurred, well, there was rainfall and flooding, and then the levees broke, and that caused additional damage. And even when you think about the repair and mitigation work that's ongoing, that work happens even today. So there are financial implications in terms of insurance or the ability to rebuild, but there are also ecological implications. Say, for example, um, if you think about the habitats for species that are necessary to sustain life in those areas or in those watersheds, there are a number of examples. So, the purpose of taking a look at these case studies was to start to think about kind of the pattern that we could use to think about community water. So, I want to introduce us to our community water project and talk about the components that you're going to need for that. And then we're going to come back and discuss um, these case studies um, and think about those a little bit further. So, this is in addition to your patterns of inquiry and your reading quizzes, the Community Water Project is the other component of your grade for this class. So, I thought it would be important to do some of our frequently asked questions and to start to talk about this project. This is due the last day of class for us. So it's a project that we'll start now and we'll continue to work on over the next couple of weeks. So there are 5 components. Each of these are worth 20 points. So there's an overview case study. So this is where you're going to record a 2-minute claim evidence reasoning statement. That oral presentation is going to be very similar to literally what we just did. So you're going to give um, an introduction to your water site, what the problem is, the evidence of that problem, and then the reasoning where you start to connect the ideas that we've been talking about in this class with your site that you have chosen to investigate. The next component is a state of water. So this is a 2 to 3 page written summary where you talk a little bit about the the state of water in that physical place. Then there is data wrangling. So this is where you have calculations or figures, you show an analysis. That's your quantitative reasoning. And then we have your proposed solutions. This is where you're doing some critical thinking about, well, how do we address that problem? And then the last piece is your references and information literacy. So we're going to talk about each of these in a little bit more depth just to make sure that you have a sense of the scope. Okay, so your case study. There are many places that you can choose. Um, I have a list of places in California. Um, if you're like, hey, I'd really rather do a place outside of California, you're welcome to do that too. But your goal for this overview of the case study is the claim. So, what's the problem or the pollutant or the issue? How does the pollutant or issue impact the community? And then the reasoning is what's the chemistry or the science that's associated with that and why? Why is it a problem? And that's a 2-minute oral presentation that you'll record. You're welcome to share slides if that's helpful for you. Pictures are really powerful. images of data are powerful, but the goal is that you'll record yourself on Zoom. You don't have to show your image of you. You can show your slides and have you talking. That's totally fine. But that's an introduction to the site that you've chosen. And then the state of water. So for the place that you've chosen, you're going to develop a water profile. So you're thinking how much water, who and what uses the water. So what's around that water? Are there cities, neighborhoods? Are there rural incorporated or unincorporated areas? Are there sources of pollutants? What are the risks or the threats to that water? And then how can we protect the water? So the state of water is the kind of written exposition that takes your case study introduction and develops it further. And then your data wrangling is going to be at least 3 concepts that we've covered in class. So things like concentration or solubility. And you're going to provide example calculations for the site that you selected using available public data. Then you're going to create 3 figures. So it could be a box and whisker plot or a bar graph or a scatter plot that tells the story of the water at your site. So it's going to be important to include your descriptive figure captions, the title, the axis labels. And then the goal is to provide a short written summary of the analysis that you conducted. What's the key interpretation from your figures? What's the conclusion or the big takeaway? Your proposed solutions then are going to be based on the problem you identified, and you need to propose at least 3 solutions. So one of the solutions must be chemical. So water purification, a treatment approach. One solution must be social. So that could be education, policy. And then the third solution must integrate another discipline or field. So you could focus on epidemiology and human health. Say, for example, when you think about the Flint water crisis and lead. Or it could be engineering. Say, for example, changing the way the levees are constructed in Pajaro. And then references. So using APA, you're going to provide a complete list of references, including relevant URLs. Obviously, you're doing in-text citations for the written components. And if you use any sources for your oral presentation, you're going to include in-text for that as well. And then you're welcome to use artificial intelligence, but you need to follow the guidelines from APA and include the prompt that you used. So I just want to take a moment and go back to our overview. Any questions about this project? Okay, hearing none, please feel free to reach out to me if you have individual questions. I'm going to give you some time between now and when we meet on Tuesday to think about the site that you want to choose. I'm going to post a list of options that you can choose from. And of course, if you have another one in mind, you're welcome to do so. Um, I think what I would like to do is take about 10 minutes and just talk about the case studies that we've talked about so far. So we can talk about the desalination plant for Monterey. We can talk about Weidren. We can talk about the Salton Sea. And we can talk about Pajaro. And I'd be curious to hear from you. What do you notice? What do you wonder as you think about those case studies? What's some of the things that come to mind?
Are they actually gonna build the desalination plant in Marina or?
Ooh, that's a good question. So at this point, they don't have a permit yet, and they can't build without a permit. But there is a lot of pressure for Marina to grant the permit, and that's the current stage that we're in. So it really comes down to, does the judge, who has now kind of ruled on the supply and demand, um, do they tick that box saying CalDAM has met the requirement? And then if they do, it's the city of Marina that has to grant the permit.
I hope they don't, because that has just so much implication for the wildlife and the marine sanctuary in Monterey Bay.
Yes, you are correct. There is a huge implication. And I think there's not just an ecological implication, There's also a financial implication. The cost of building the desalination plant is huge, and that means that residents of Marina will have to bear part of that cost. So Cal Am would pay for some of the cost, but the rest of it would actually come from the residents in Marina, which is interesting because likely they would not use the water that is being generated by the desalination plant. Likely it would be primarily folks on the Monterey Peninsula that are using that water. So it's got a lot of complexity as a problem.
That's crazy.
Yeah, it is a really interesting space. I think the dilemma is though that the existing solutions or the solutions that folks have been working on so far other than desalination are not enough. Like right now, you cannot get a permit to build on the peninsula. Say for example, you wanted to build a house because there's not water available. So because we don't have enough water to meet the existing need, adding a new need has been denied. So people can't get building permits because there isn't enough water um, to meet a new build, which is another dilemma associated with that space. And that's not just residential, that's lots of other building projects. So that could be impacting, say, for example, tourism and the hotel industry. What are other thoughts as you think about these potential cases? What comes to mind? What are you thinking about? Let's try this. Choose a case study other than the one that you reviewed. So choose one that you are not as familiar with and put in the chat one question that you would ask. So if you're like, hey, this is a case I'm not as familiar with, but I have questions, what is a question you would ask? So for example, I'm not as familiar with the Pajaro Levee project, so I'm curious, what is the current state of rebuilding the levees in Pajaro? If, say, for example, we were to get another atmospheric river, would there be levees to prevent additional flooding, or are those things that have not yet been fixed? So that's a great example of a question that I'm curious about. What are questions that you are curious about? One of the questions that I got in the chat that was sent directly to me, someone asked, oh, well, is the gas contamination that happened in Weedron common? Because people store gas everywhere. So is it possible that you could have gas that leaks into a water supply and it's just a smaller amount so you don't notice? The Weedron was a lot, but we have gas storage everywhere. Is it possible that there's gas in the water and it's just present in an amount that we can't smell? And I feel like that's a really good question. I don't know the answer to that, but I can do some research and get back to you. I wonder if there are protections that gas storage facilities have to have in place to prevent water contamination. But I don't know. So I'm going to do some additional research and get back to you. Ooh, Sydney, such a good question. What are the health risks implications of increased benzene levels? Yeah, I know that benzene is a carcinogen. And so I think exposure to benzene, especially if it's chronic exposure, has a greater risk of causing cancer. But there might be other health concerns that are associated there that I'm not as familiar with. And so I think it's certainly a concern. There are examples of human exposure to certain chemicals. So I think the one that is more familiar to folks, I think the Aaron Brockovich, where they looked at chromium exposures, hexavalent chromium specifically, um, is one that essentially people who were living had water that was exposed to chromium 6 levels, and that led to an increase in a variety of health concerns. Some of those were cancer. So that would be another example. There are definitely human health implications for sure. So that's a great question. Thanks for asking. Any other questions that you can ask related to the case studies that we're taking a look at? The last one that I'm going to have you take a look at. So I just want to share this. I was looking at our um, patterns of inquiry, and this is one that you had for concentration. And I just wanted to go over this solution because I think several folks got hung up. They made it part of the way through the calculation, but then towards the end, I want us to check our assumptions. So you all did a great job at determining the 15% solution is 15 grams per 100 milliliters. And then being able to figure out how many grams total are in 400 milliliters, most folks were able to do without error. And then I was pleased to see the calculations in terms of molecular weight. But then actually the calculation of the number of moles, this is a step that not everyone did, and I think sometimes that ended up being the sticking point, but here's the number of moles. And then the osmoles for a 400 milliliter magnesium chloride solution, there's 1 magnesium and 2 chlorides, so that's 3 osmoles total. So we're going to convert our moles to osmoles, so 0.63 times the 3 moles gives us 1.89 osmoles. But then the last piece, this calculation of the osmolarity, this is the number of osmoles in 400 milliliters. We would need to figure out how many would be in 1 liter. So that's our final conversion step. So 1.89 per 400 milliliters. And right, we need to convert that to liters. So that would be osmoles per liter for our osmolarity, or 4.73. So I just wanted to make sure that we touch base on that work solution. I've sent that out to a couple of you to take a look at. If you could compare your process and just think about where your potential source of error is, I would appreciate it. And then the last piece that I want us to take a look at. So in Canvas, you will find the information that we talked about today for each of the case studies, as well as the information about desalination. So that's our worked example. But I have a couple of resources for you. So there's an introduction to the CSUMB library and access to information from there. And then there's also the information literacy resources. So those are available for you. Um, don't forget to do your exit ticket for this week. And then I'll send out by email a list of possible sites in California for you to consider as you're thinking about what watershed you want to study. So your pattern of inquiry for buffering is going to be due on July 7th. Because of the holiday weekend, I'm not assigning a new pattern of inquiry. We'll take a look at that next week. So the only thing that's due for you is what we've already worked on this week. You don't have anything else that's new. We'll make our selection for the site that you're going to study when we meet on Tuesday for your community water project. So be thinking about what you want to do, and keep a lookout for the email with the list of potential sites. And then the last piece that I think is really important to just consider is as we think about kind of the state of water, one of the things that is just, it's tricky, right? So O.B. Kaufman does this really beautiful work in this book, The State of Water. If you don't have access to it, I've done a little bit of an introduction. This is the prep for what we're going to talk about next week. So you're going to be talking with a partner about the state of water in California. We're We're going to take a look at these statements. I want you to have the chance to see this ahead of time so that when you talk with a partner, you have a chance to, if you're like me, sometimes I need time to think and process. So this is available for you to take a look at. These are the conversations that we're going to start having on Tuesday next week. We're going to look at what a watershed is. And then we're going to talk about different types of measurements. So million acre feet, for example. And then there's not a sign up for exam 2. We're not doing exams for this, but we are going to sign up for your community water project. So fret not, you're going to get a list, and here are some of the examples of watersheds that are available in California. You'll get to choose. There are many that are associated with rivers. That's another option too. And then you might say, for example, be really interested not just in rivers, but in other types of water associated with California. So I've got some resources that are available here too. So no exam, hooray for that. But we are going to work on our community water project next week. If you have any questions, please don't hesitate to reach out to me by email. Otherwise, I wish you all a wonderful 4th of July, and I look forward to seeing you next week. Thanks again.
Bye. Thank you.
Thank
Have a
you.
great one. Take care.